Dum-de-dum. Good morning, everyone. Wait for some more people to join in. Oh, good morning. Hello. Oh, you know what? I want to get set up. Go to. Let's see. Just getting some stuff set up while I wait for people to join in. Hello. Greetings and salutations. We'll wait for like 2 more people. I cannot stop yawning today. I don't know about you guys, but Thursday is the hardest day for me to wake up in this schedule. Okay. Let's go ahead and get started. Hope you guys are doing well. In the last lesson, we learned about what a force is, and we learned Newton's laws of motion. Okay. Today, we are going to learn first about the different types of forces that we will encounter. Okay. The different types of forces. That's the first thing we're going to talk about. And then in the second half of the lesson, we will talk about what is called equilibrium. So, what are some of the types of forces that we will encounter in this class? And this first part is going to be mostly review for many of you. So the first type of force that we're going to discuss is weight, the weight force, which is denoted by W. And the size of the weight force is the object's mass times the acceleration due to gravity on that particular. Oh, hey there. We have a student who's not in the class, but is just popping in. Thanks for watching. All right, so weight is an object's mass times the acceleration due to gravity at its particular location. Okay, so for example, if you are on Earth, the acceleration due to gravity is 10 meters per second squared on Earth. And if you take that and you multiply by gravity, or by the object's mass, by gravity, you get its weight force. That's the force of gravity, is the weight force. Okay. Gravity points downward, so if we wanted to put this in, like a vector form, if we wanted to, we could say W vector equals minus mg times j hat. So it points in the negative j direction. So that's if we have a problem that's fully two-dimensional and we need to use vectors. If it's a one-dimensional problem, you don't need to use vectors. But if it's two-dimensional, you might want to do that. Okay. One of the things about the weight force is that your weight can change from place to place. If you go to a new location, you might have a different acceleration due to gravity, so your weight can change. However, your mass is a property of you, okay? So your mass stays the same if you go from place to place, but your weight could change if you go from place to place. All right? The second force that we will encounter is called the normal force. Which is, if you're in the IB class, then the normal force is called the reaction force by the IB curriculum, okay? And I will denote it by N, or maybe I'll denote it by F sub N, just to F sub N. And it is the force that keeps you from passing through a surface. So let's do an example involving the normal force, okay? Let's suppose you have a floor. Here's a floor. And you have a 5 kilogram block that is sitting on the floor. In that case, you can see that gravity is pulling down with 50 newtons of force. Where did I get 50 newtons from? I got it from mass, which is 5, times gravity, which is 10. The normal force, so what would happen if there was no normal force? Well, this 5 kilogram block would accelerate through the floor and go down. So the floor is exerting an upward normal force, F sub N, in order to keep you from passing through the floor, okay? And it turns out that the normal force must be equal in size to the weight force in this case. Why? Because what if the normal force were greater than the weight force? That would mean that the block is accelerating into the air. What if the weight force was greater than the normal force? That would mean that the block is accelerating into the ground. So the fact that the block is just sitting here means that we must have a normal force of 50 newtons upward. Okay? So very often, the normal force is going to be equal to the weight. If you have no other forces besides these two, then they kind of tend to cancel each other out if something is just sitting on a surface. However, do not be tricked. Do not be tricked, because sometimes the normal force is not equal to the weight force. I will give some examples of that. What if we had this same What if we had this same 5 kilogram block, but we added an additional force? What if we have an applied force of size, let's say size 100 newtons. Actually, not 100 newtons, that's too much. Let's say 70 newtons. And that 70 Newton force acts at an angle of 30 degrees to the horizontal. Okay? What is going to be the normal force in this case? Well, how much force is pulling upward in this case? The amount of force that's pulling, so because this is a diagonal force, it's partially pulling upward and it's partially pulling to the side. Okay? So how much force is pulling upward? Well, that would be 70 sine of 30 degrees because it's opposite. Okay? Which is 35 newtons. So there is 35 newtons pulling upward. Okay? So if we were to draw a diagram of the upward and downward forces, we've got a 50 Newton downward force from gravity. We've got a 30 Newton upward or 35 Newton upward force from that applied force. And then we have the normal force. So how big does the normal force have to be in order to prevent the block from going down into the ground? Well, we can see that if I didn't have the normal force, there's 15 newtons of downward force. So that means that the normal force must be 15 newtons of upward force in order to prevent the block from going through the surface. Okay? So you got to be a little bit careful. If there are other forces involved that are pushing something into a surface, then the normal force is not going to be equal to the weight. All right? I can give you another example. What if you were holding something against a wall? Like this. Maybe you have a 5 kilogram object and you're holding it against the wall with a 10 Newton force. So you're pushing it up against the wall with 10 newtons of force. What's going to be the normal force in this case? Well, in this case, because the wall is vertical, the normal force actually acts horizontally. Okay? So if we were to look at the forces that are acting on this 5 kilogram block, it's got a 50 Newton weight force. It's got a normal force which is pushing away from the wall. And it's got a 10 Newton applied force. Okay? Now, it turns out that the 50 Newton force is not making the block go into the wall. You get what I'm saying? The 50 Newton weight force is sliding the block along the wall. So that force doesn't matter. Really, what does the normal force have to be in order to prevent the block from moving into the wall? It's got to be 10 newtons. Because it's the 10 Newton force that's the one that's actually pushing the block into the wall. Okay? So these are some different scenarios. These two scenarios are some scenarios where the normal force is not equal to the weight. I even got one more for you. What if you're in an elevator and the elevator is accelerating upward? This person, so if this person is in an elevator that is accelerating upward, then the normal force has to be bigger than the weight force. Why? Because if the normal force was not bigger than the weight force, the person would not be accelerating up with the elevator. Okay? So normal and weight force are not necessarily equal to each other, but oftentimes they are. All right. The next force we're going to talk about is called the friction force. Okay. The friction force, there are two types of friction. There is what's called static friction. Okay. And static friction is basically the force that must be overcome to budge the object. Okay? If something is not moving, like my coffee mug here, my coffee mug is not moving. If I apply a force, the force I have to overcome to make the coffee cup move is static friction. Static means at rest. So it's the frictional force if you're pulling on something but it's not moving yet. So I'm applying a force but the coffee mug is not moving. That's because I haven't overcome static friction. Okay? So it's the force you have to overcome to budge the object. Kinetic friction okay? Kinetic friction is the force to keep an object sliding. Okay? So these are two different forces. The force required to get something moving to begin with is usually larger than the force required to keep something moving. So it's harder. Do you ever notice that when you're pushing something that's heavy, it's like you have to push really hard at first, and then it budges, and then once it budges, it's fairly easy to keep it moving. So to make it start moving, you need to overcome static friction, but to keep it moving, you have to overcome kinetic friction. So usually friction is denoted by a script F. Okay. And we'll put F sub S for static friction and F sub K for kinetic friction. So the formula for kinetic friction is mu sub K times the normal force, where mu sub K is called the coefficient of kinetic friction. Okay, so the coefficient of kinetic friction is basically telling us the roughness of the surface. Okay, the smaller the coefficient of friction is, the less friction force you have, the slipperier the surface is. Notice how friction depends on normal force. If you take your hands and you rub them together, and you're pushing your hands together lightly, it's pretty easy to rub them together. Pretty easy to overcome friction. But if you push your hands together, okay, it's harder to slide them. More normal force means more friction. Okay. Static friction is a little bit trickier. Okay. Because there's a maximum static friction. The maximum static friction is mu sub S times normal. So mu sub S is called the coefficient of static friction. And these are two different coefficients. Because as I said, the force required to keep something moving is usually different from the force required to start it moving to begin with. Okay? Let's do a little example. We've got a box. Let's continue with our 5 kilogram box. Okay. Let's suppose that for this particular interface, we have mu sub K equals 0.5 and mu sub S equals 1.0. All right? And we pull with a force F. We pull horizontally. We're trying to overcome friction. In this problem, because there are no vertical forces that are changing the normal force besides gravity, for this problem, because there are no additional vertical forces besides gravity, we are going to have that the normal force equals 50 newtons, just like we have in this example, okay? Because there are no other forces no other vertical forces that are going to change it from that. We apply a force F, that's an applied force, all right? So How much force is required to budge this box? Well, it would be mu sub s times normal. So mu sub s is 1, and the normal force is 50. So what if the applied force is equal to, let's say, 40 newtons, 40 newtons is less than 50 newtons. So there is not enough force to budge the box. So that means there is going to be no motion. Okay? What if we applied 60 newtons? 60 newtons can budge the box. So the box is going to start to move. Okay? The box moves. Once the box starts moving, we're going to have kinetic friction. Mu sub k is 0.5, so we're going to have 0.5 times 50. So we will have 25 newtons of kinetic friction. So we're pulling this thing with 60 newtons of force, and friction is fighting us with 25 newtons. So if we wanted to write Newton's second law, the net force would be 60 minus 25, and that would equal ma, so that would equal 5a, so we could calculate the acceleration of the box. There's a comment. So the applied force is 60, but the normal force is still 50. So this would be 0.5 times 50 still. Okay. So that's a little bit about how the friction force works. Okay. There's another force called tension. Tension T, which is the force from a rope. Not enough sleep. I hear you. Okay, that's all I'm going to say about that. I'll do the Forrest Gump thing, and that's all I have to say about that. And then we have the elastic force. Okay, the elastic force is equal to K times X. So I'll just say F sub E for elastic. And so X is the amount that something is stretched or compressed. Okay, so I don't have any rubber bands here. Bummer. If you think about a rubber band is flimsy and it doesn't resist being stretched until it's completely taut. And then once you pull it further, then it exerts an elastic force. Okay? So X is referring to basically the amount that is beyond taut. Okay. So if you have a rubber band that has a natural length of 5 centimeters and you stretch it so that its total length is 7 centimeters, then the X value you would use is 2 centimeters. Okay, so it's how far beyond its natural length have you stretched it. Okay. K is called the stiffness. All right. Units of K are newtons per meter. All right. So that's it for forces. So now let's talk about something called equilibrium. And in particular, this is translational equilibrium. Okay? Translational equilibrium. So equilibrium means that the net force as a vector is equal to 0. Okay? So basically that is going to mean that the object has a constant velocity. And generally speaking, so if you are doing any kind of like structural engineering, okay, then the structure is in equilibrium, which means the net force is 0. So it has a constant velocity. Typically speaking, that velocity is 0. If you're talking about a building in equilibrium, the constant velocity that it has is 0. So I'm going to put usually 0. Usually that constant velocity is 0. So let's do an example of equilibrium. All right. Suppose we have a ceiling okay, and you have a giant sign. Let's suppose that it is it's a 50 kilogram sign. Let's make it a mega sign. It's a 50 kilogram mega sign. There you go. It's almost November. One of my neighbors has a giant mega flag. It's a flag. It's not a 50 kilogram sign, but whatever. And let's suppose that this sign is supported by 2 ropes. So there's 2 ropes. And so those ropes are the things that are holding up the sign. Okay, so each of these ropes, what is the force from a rope? It's a tension. So there's going to be a tension T1, and there's going to be a tension T2. All right, and these ropes, because of the way the sign was hung up, the ropes are making different angles. Okay, so this angle right here is 45 degrees. And this angle right here is, let's say, 60 degrees. Okay? And we want to figure out what are T1 and T2 if the sign is in equilibrium. Okay? So how would that work? Well, I'm going to draw what is called a free body diagram. Okay? And that's just I'm going to represent the sign as a dot, and I'm going to put some forces. I'm going to put all the different forces that are acting on the object. So I have T2, I have T1. I'm going to put these angles in here. So I have 45 degrees, and I have 60 degrees. And then I have the weight force, which is going to be 500 newtons. Okay? The mass is 50 kilograms, so 500 times 10, which is gravity. Okay? Now I'm going to take this, And I'm going to take the diagonal forces and I'm going to turn them into vertical and horizontal forces only. Okay? So the vertical component of T2 would be T2 sine of 45 degrees. Where'd my calculator go? There it is. There's my calculator. And so I'm going to type in, what is the sine of 45? And it's 0.71. See that? So the vertical component of this is 0.71 T2. The horizontal component is going to also be 0.71 T2 because sine and cosine of 45 are equal. For the 60-degree angle, so the vertical component of this would be T1 times sine of 60. So what is the sine of 60 degrees? It's 0.87. So this is 0.87 T1. And this is going to be T1 cosine of 60, which is going to be 0.5 T1. Okay? So I'm going to draw this a little bit bigger. Whoa, what just happened there? So here is my dot. And I'm going to take those diagonal forces and I'm going to write them as a vertical force and a horizontal force. So this force, T2, is equivalent to an upward force of size 0.71 T2 and a rightward force of size 0.71 T2. Okay? The 60-degree force is equivalent to a 0.87 T1 force going up. And a leftward force of 0.5 T1. And then, of course, there is a 500 Newton force going downward. So, we're trying to figure out T1 and T2. Well, we know that this sine is in equilibrium. Okay? So that means that the net force in the vertical direction must be 0, and the net force horizontally must be 0. So if the net force horizontally is 0, then that means that this rightward force had better be equal in size to that leftward force. If they're not equal in size, then there's a net force horizontally. Okay? So I'm going to get an equation. So the net force in the x direction being 0 implies that 0.71 T2 is equal to 0.5 T1. Okay? Then, the net force being 0 in the y direction implies, now how much upward force do I have? I have 2 upward forces, so that means that 0.87 T1 and the other upward force, which is 0.71 T2, has to equal the downward force. Okay? So we have 2 unknowns, T1 and T2, and we have 2 equations. So this is a system of equations for T1 and T2. So you can solve it. One of the ways you can solve it is by substitution, also known as Gaussian elimination. So, we could write T1 equals something as a function of T2 and then plug that into this equation and then solve for T2 and then plug that back in to solve for T1. We could do that. I'm going to solve this using Desmos. Okay. So if I use Desmos, I'm going to put T1 on the horizontal axis, and I'm going to put T2 on the vertical axis. And then I'm going to type in my two equations. So my first equation is 0.71 T2 equals 0.5 times T1. So that's a line. And then I have a second equation, which is 0.87 T1 plus 0.71 T2 equals 500. Okay? So the second line is there. It's just, I'm going to zoom out. Okay. So there's the second line. And the intersection is the solution. So let me click on that. So we have T1 is going to be 365 newtons. And T2 is going to be 257 newtons. Okay? So there you have it. That's the answer. Generally speaking, whichever rope is more vertical is going to be the one that is bearing more of the load. So the 60 degrees from the horizontal is more straight up and down than 45 degrees. So the T1 is going to be holding more of the weight. Now, what if we solved this and we said, whoopsies, these ropes can only hold 300 newtons. Actually, one of the things, if you go to to Home Depot or Lowe's or whatever, and you buy rope, one of the specifications is how many pounds can this rope hold, okay? So what if you held up this sign and the rope can only hold 300 newtons? Then the T1 rope is going to break, okay? So this rope is going to break. And then if this rope breaks, then you can imagine the sign would swing down vertically. And then the rope T2 is holding all the weight. So T2 would have to be 500 newtons. And then T2 would break, even though T2 started out as being less than 300 newtons. But once T1 breaks, then T2 is doing the entire job, and then T2's tension goes above 300 newtons, and then that one breaks as well. So you can often see this. It's kind of called a cascading failure, right? It's one thing breaks, which means that the other stuff then has to pick up the slack, which means something else breaks, which means everything else has to pick up even more slack, and then it cascades, and you eventually have just complete failure. Okay? So that is my lesson for today. So I will see you in the Zoom room. Okay? Bye for now.